All right, this is the first video for section 5.4 in AP Calculus, which is where we learn the fundamental theorem of calculus, which is all about integrals. So we're going to begin by kind of looking backwards, and this is something we've been talking about already within this unit and in previous units. Back in chapter 4, we talked about this as well. So here I've got three different derivatives that I've given you, and we want to come up with what the original function is that it came from. So for example, the first question, f prime of x is equal to x. Well, I know that if f prime of x is equal to x, then f of x would be equal to the integral of whatever f prime is, so in this case x, with respect to x. So we would call it x dx. So to integrate that, if x to the first is the derivative, then that would mean that the original would have had to have been an x squared. But then we have to think about the coefficient. The coefficient on f prime is a 1. So in order to take the derivative of x squared and end up with a coefficient of 1, we would need to think through what would have had to have been the coefficient on the x squared in order to make that happen when we do the power rule. So if we bring the 2 in front, 2 times what would give me a power, or give me a coefficient of 1? So that would be a 1/2. Another way that you could think through that is to take the old coefficient divided by the new exponent, and that will tell you what your new coefficient would be. So 1 divided by 2. And then since this is a general solution, it could have any constant at the end of it, and that would be our original function. So f of x is equal to 1/2 x squared plus c. So now I want you to pause the video for a minute, and I want you to try number 2 and number 3 and see if you can figure out what function they came from. Okay, so if you look at my work there, then hopefully you realize that example 2, or that number 2 there, if f prime of x is equal to sine of x, then the original function is negative cosine of x plus c. You always want to put that plus c at the end of indefinite integrals. And then for f prime of x equals negative 1 over x squared, I rewrote that as negative x to the negative 2. And then I could use the reverse power rule on it, just like I did back on number 1. So you end up with x to the negative 1 plus c, or 1 over x plus c. So that essentially is the first part of the fundamental theorem of calculus. It says that if a function is continuous on a closed interval from a to b, then the function capital F, or big F, is equal to the integral from a to x for f of t, little f, of t dt. And it has a derivative at every point in the closed interval from a to b. And the derivative is essentially equal to the derivative of the integral, which would mean the inside function. So the inside function is the derivative. The outside function is the original, if you want to think about it in last semester terms. But that only works if we're taking the derivative from a number, an a value, to a variable x. So we're going to look at some examples of that in just a minute. So what exactly does this part 1 of the fundamental theorem of calculus mean? Well, it means that every continuous function f is the derivative of some other function. So every function is the derivative of something else. And every continuous function has an antiderivative. So that means every continuous function I can integrate and work backwards and figure out what it is the derivative of. Essentially what that means is that integration and differentiation are inverse processes, where differentiation takes us down a level, kind of like how you go from position to velocity to acceleration, then integration takes us up a level. So we could go from acceleration to velocity to position. You could kind of think about it in physics terms that way. So for example, we want to take the derivatives of these integrals. So my first example here, number 1, I want to find the derivative with respect to x of the integral from pi to x of sine of t dt. So notice that this is a value, a numerical value, and this is a variable. If that's the case, then your derivative is simply to take this and replace it with whatever the variable is. But that also means that t is going to get replaced. So that would become sine of x, and then times the derivative of whatever is up here. But the derivative of x is just 1. So my answer would be sine of x. So then on something like number 2, we want to find the derivative of this integral. Notice that it starts at the variable and goes to the number. So that would be the same as, remember, order of integration? If we reverse the order, then we change the sign. So that would be the first thing that I would want to do, is change the sign of that so that it starts at a number and ends at the variable. Then we do it pretty much the way that we did example 1. The derivative would be to take whatever was inside of the integral, but replace all the t's with what's up here. Now, we still have the negative out in front, so that would be x sine of x times the derivative of x, which is just 1. So the derivative would be negative x sine x. Now, this third one here, we do start at a numerical value, but notice we don't end just at x. We end at x squared. So when we're taking the derivative of that, this is why it's so important that you understand that you're replacing everywhere that there's a t, you're replacing it with what was up at the top of the integral. So that includes the derivative of t means to take the derivative of x squared. So this would be times 2x. And if you want to clean that up at all, that would be 2x times the square root of negative 7 plus, remember when we have a power to a power, we multiply those. So that would be plus x to the 6th. And that would be the answer there for example 3. So that's the concept of the first part of the fundamental theorem of calculus as far as taking derivatives of integrals and how that works. The second part of the fundamental theorem of calculus is how to evaluate definite integrals where both of the boundaries are numerical. We've already kind of done these as we've been doing area under a curve. So we're just going to kind of look at a little bit more with it today. So the integral from a to b for a function, a little f, means to integrate it back to the original function it came from. We substitute in the upper boundary first, minus substituting in the lower boundary second. So you figure out what function it came from, then you substitute in and do upper substitution minus lower substitution. So what that means is that any definite integral of any continuous function can be calculated without having to use limits or left bound rectangles, right endpoint rectangles, midpoints, trapezoids, none of that. If we can algebraically integrate the function back to the function that it came from, then we can always find the exact area under the curve using this integration process instead of the approximation by the rectangles and trapezoids and things that we've been using so far, or even just basic geometry formulas. We don't have to use those if we can algebraically integrate. So, for example, I want to evaluate using an antiderivative the integral from negative 1 to 3 of 3x squared plus 1 dx. So this is just sort of a basic one to help us understand what's going on here. So the first thing that I would do is I would take what's inside of here and I would figure out what that is the derivative of. So x squared would have come from x to the third. The coefficient in front, if I take old coefficient divided by new exponent, 3 divided by 3, so that would give me a 1 for my coefficient. So 3x squared is the derivative of x cubed. Bring my plus sign. 1 would be the derivative of an x. And then I have my boundaries from negative 1 to 3. So the way that substitution works, we're going to substitute the 3 in first, and then we're going to substitute the negative 1 in. Now, honestly, sometimes I find it's better to work those out individually and then worry about the fact that we're subtracting them. So this is 27 plus 3 is 30. This is negative 1 minus 1, so negative 2. Then it would be 30 minus negative 2. Okay, so then we get a 32 for our final answer. Some people have trouble with that because they forget that they're subtracting that entire second substitution. So that's why it can often be helpful to substitute the top all by itself, substitute the bottom all by itself, and then subtract top minus bottom after you have substituted. So that's where we're going to end the first video for the fundamental theorem of calculus. The second video will pick up with how to find total area.